our portion is Lewis symbols or Lewis dot symbol. These are simple notations or representations used to represent valence electrons in an atom. In this representation, first you should write the symbol of that element and it is surrounded by the number of valence electrons. We can discuss it with examples. First one, lithium. Lithium, you know, the atomic number of lithium is 3. Then you write the electronic configuration 1s2, 2s1. Then the valence shell consists of, this is the valence shell, 2s1 consists of 1 electron. So the number of valence electrons or outermost shell electrons in lithium atom is only 1. So it is represented like a dot in lithium atom. So first you should write the symbol, that is Li. Then one dot is right surrounding it. This is the Lewis dot symbol or Lewis symbol. Then next another example, beryllium, atomic number 4. Then the electronic configuration is 1s2, 2s. The valence shell is 2s, consists of 2 electrons. Then the Lewis dot symbol is, first write the symbol of beryllium, which is Be, then 2 dots. Clear? 2 valence electrons. It represents the valence electrons, not total electrons, only valence electrons. Then next, boron, atomic number 5. Then 1s2, 2s2, 2p1. Then the total number of electrons present in the valence shell is, the valence shell is the main shell, that indicate the principal quantum number, that is here n is equal to 2. So this is subshell, S and P are subshell, the main shell is here L shell, K, L shell, that is n is equal to 2. So this is the main shell. The main shell consists of 3 electrons. So main shell electrons are valence electrons, so consist of 3 electrons, 2 plus 1. So the number of valence electrons present in this boron atom is 3. So write the symbol B, boron, then 3 dots. 3 electrons, not misunderstand, this 2p only consists of 1 electron. This is not the outermost shell, this 2s and 2p including in the outermost shell, main shell. So this consists of 3 electrons, 2 plus 1. 2s consists of 2 and 2p consists of 1. Total 3 electrons, so 3 dots. Next, carbon 6. 1s2, 2s2, 2p2. Then the valence shell consists of, main shell consists of 4 electrons, 2s consists of 2 electrons, 2p consists of 2 electrons. So total 4 electrons. So the number of valence electrons are 4. Then 4 dots surrounding the symbol of carbon, 4 dots. Then nitrogen, 1s2, 2s2, 2p3, atomic number 7. Then the valence shell electrons are 2s2, 2p3, total 2 plus 3, 5 electrons. So first you should write the symbol of nitrogen, that is N. Then write the 5 valence electrons, 1, 2, 3, 4, 5 dots. Next one, oxygen, atomic number 8, 1s2, 2s2, 2p4. Then the valence shell consists of 6 electrons, 2 plus 4, 6 electrons. Then first you should write the symbol O, then 6 electrons, 1, 2, 3, 4, 5, 6 electrons. This is the Lewis dot symbol. Then next one, fluorine, atomic number 9, electronic configuration 1s2, 2s2, 2p5. Then the total number of valence electrons are in 2s 2 electron, 2p 5 electrons. Total 2 plus 5, 7 electrons. So here first write the symbol fluorine F. Then 7 electrons. 1, 2, 3, 4, 5, 6, 7 electrons, 7 dots. Then neon, atomic number 10. Then 1s2, 2s2, 2p6 is the electronic configuration. Then first this consists of 8 valence electrons. So this is a noble gas. So consists of 8 valence electrons. So neon symbol, then 8 valence electrons. 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. This representation is known as Lewis dot symbol. So we can write the Lewis representation for molecules also. Some examples we can discuss here. First one, hydrogen molecule. Hydrogen, you know, one hydrogen atom, one electron, valence electron. Then other hydrogen atom, one valence electron. They are mutually shared. Then we get hydrogen molecule. Then oxygen molecule, one oxygen atom, you know, valence, how many valence electrons? Yes, 6 valence electrons. So 6, 1, 2, 3, 4, 5, 6. Then next oxygen atom, 6 valence electrons. Then each oxygen atom need 2 more electrons to complete their octet. Then here sharing of 2 electrons takes place to form a double bond. In nitrogen molecule, nitrogen, you know, nitrogen, the valence electrons are 5 valence electrons, 5 dots. Then one nitrogen need 3 more electrons to complete their octet. So one atom share its 3 electrons to neighboring nitrogen atom to form nitrogen-nitrogen triple bond. We can draw the Lewis representation of carbon dioxide molecule. You know, draw oxygen, how many valence electrons? You know, 6 valence electrons. Then oxygen need 2 more valence electrons to complete their octet. So carbon 2 electrons for mutual sharing. Then this oxygen atom also have 6 valence electrons. This carbon atom have 4 valence electrons. 4, 2 plus 2, 4. Then here this oxygen carbon mutual sharing bond. Here mutual sharing is carbon and oxygen. Double covalent bond is formed and there is 2 double covalent bonds are formed and they complete their octet. This oxygen, listen, oxygen, how many electrons are surrounded? Listen, oxygen 1, 2, 3, 4, 5, 6, 7, 8 electrons. Then this carbon, how many electrons are surrounded? 1, 2, 3, 4, 5, 6, 7, 8, 8 electrons. Then this oxygen, how many electrons? 1, 2, 3, 4, 5, 6, 7, 8 electrons. So all atoms complete their octet and form carbon dioxide molecule. Next we discussed about the limitations of octet rule. Then what do you mean by octet rule? Yes, atoms can combine either by transfer of valence electrons from one atom to another or by sharing of valence electrons in order to have an octet in their valence shell. Then they become more stable. This rule is known as octet rule. So these octet rules have some limitations. That means some molecules do not follow this octet rule, but they are stable in nature. First one is the incomplete octet of the central atom. That means in some molecules or compounds, the number of electrons surrounding the central atom is less than 8. For example, beryllium hydride. You know, beryllium, how many valence electrons? Atomic number 4. Beryllium, 2 valence electrons. So, dot representation beryllium, 2 valence electrons are here. Then, hydrogen, you know, Lewis representation, hydrogen 1 dot. Here also 1 hydrogen, 1 dot. Then here beryllium, share its 1 electron with the hydrogen atom to form a single covalent bond. Similarly, here also form a single covalent bond. Then listen, hydrogen here complete their doublet, means it consists of 2 electrons. 2 electrons, these are hydrogen become more stable. The valence shell consists of 2 electrons, then they become more stable. So hydrogen complete their doublet. Here also hydrogen complete their doublet, 2 electrons. But in the case of beryllium, you can see 1, 2 beryllium surrounding this beryllium atom. How many electrons are there? 1, 2, 3, 4. Only 4 electrons are surrounded by this beryllium atom. That means beryllium do not complete their octet. So this is one violation of this octet rule, beryllium hydride. Next one is boron trichloride, BCl3. In the case of BCl3, boron, you know, atomic number 5, that consists of 3 valence electrons. So boron 3 dots, 1 2 3 dots, boron 3 valence electrons. Then these 3 valence electrons are shared by 3 chlorine atom to form 3 single covalent bond. Then here you can see boron share its one electron with one chlorine atom. The chlorine consists of 7 valence electrons. Then here chlorine complete their octet. 1, 2, 3, 4, 5, 6, 7, 8 electrons. This chlorine also complete their octet. 1, 2, 3, 4, 5, 6, 7, 8. Then this chlorine atom also complete their octet. 1, 2, 3, 4, 5, 6, 7, 8. Then listen here, boron. Boron, how many electrons are surrounded? This 1, 2, 3, 4, 5, 6. Only 6 electrons are surrounded by this boron atom. So it does not complete their octet. So this is one other example for incomplete octet of the central atom. That is the limitation of this octet rule. Next limitation is the expanded octet. Expanded octet means in some compounds the number of electrons surrounding the central atom is more than 8 electrons. The number of electrons surrounding the central atom is more than 8 electrons. That is expanded, more than 8 electrons. For example, sulfur hexafluoride, SF6 molecule. You know sulfur atomic number 16, the electronic configuration 1s2, 2s2, 2p6, 3s2, 3p4. Here 6 valence electrons are present, 2 plus 4, 6 valence electrons. So first write sulfur, then 6 valence electrons are surrounded, 1, 2, 3, 4, 5, 6 valence electrons. These 6 valence electrons are covalently bonded with the neighboring 6 fluorine atom. Here fluorine complete their octet by bond formation by sharing one electron with sulfur. This fluorine atom complete their octet 1, 2, 3, 4, 5, 6, 7, 8, and similarly all fluorine atom complete their octet. You can see in the figure all fluorine atom complete their octet. But in the case of sulfur, how many electrons are surrounded? This sulfur, the number of electrons are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons are surrounded by the sulfur atom. This is more than 8 electrons. So this is known as expanded octet. Other example is PCl5. Phosphorus pentachloride is another example for this expanded octet. The next one is odd electron molecule. The molecule with odd number of electrons are known as odd electron molecule. For example, nitric oxide molecule. You know, nitrogen 5 valence electrons. 1, 2, 3, 4, 5 valence electrons. Oxygen 6 valence electrons. 1, 2, 3, 4, 5, 6. This oxygen share its 2 electrons to this nitrogen atom to form a double covalent bond. Then oxygen complete its octet. But in the case of nitrogen, how many electrons are surrounded? 1, 2, 3, 4, 5, 6, 7 electrons are surrounded. That means 7 electrons means odd electrons, odd number of electrons. This is not complete the octet. So this is an example for odd electron molecule. Next limitation, according to octet rule, noble gases are chemically inert because they complete their octet and they do not take part in any chemical reactions according to octet rule. However, some noble gases form their compounds. For example, HCF2, KRF2, HCOF2, etc. Next limitation, this theory does not account for the shape of the molecules. Then the last one, this theory does not account for the energy of a molecule. So these are the important demerits of this octet rule. So what are the important limitations of octet rule? Yes, first one, incomplete octet of the central atom. Second one, the expanded octet. Third one, odd electron molecule. Fourth one, noble gas form their compounds. Fifth one, the theory does not account for the shape of the molecule. Last one, this theory does not account for the energy of a molecule. Next, our topic is bond parameters. Bond parameters includes bond length, bond angle, bond enthalpy, and bond order. First one, we will discuss about bond length. Bond length is the equilibrium distance between the nuclei of two bonded atoms in a molecule. That means the atoms consist of a nucleus. The distance between the center of nuclei of two bonded atoms in a molecule is known as bond length. Here you can see two bonded atoms. Here the distance between the nuclei of two bonded atoms is known as bond length. Here the bond length R is equal to RA plus RB, where capital letter R is the bond length and RA and RB are radius of atoms A and B respectively. So bond length is generally measured in picometer. Then the bond length of some molecules are given in the table. Listen carefully the values. Next parameter is the bond angle. It is angle between the orbitals containing bonding pair of electrons around the central atom in a molecule or a complex ion. So listen, for example, in the case of water molecule, two OH bonds are present. So in between them, a angle is seen. This angle is known as bond angle. So bond angle is the angle between the orbitals containing bonding pair of electrons. The bond angle of water molecule is 104.5 degree. Next bond parameter is the bond enthalpy. Bond enthalpy means bond energy. It is defined as the amount of energy required to break 1 mole of a bond of a particular type between two atoms in a gaseous state. The unit of bond enthalpy is kilojoule per mole. For example, hydrogen molecule, the bond enthalpy is 435.8 kilojoule per mole. This means hydrogen molecule can be break down into hydrogen atom, then 435.8 kilojoule per mole energy is required. Note the point, for a bond breaking, energy is required. It is an endothermic process. Energy is absorbed during bond breaking. So the bond enthalpy of hydrogen molecule is 435.8 kilojoule per mole. That of oxygen molecule is 498 kilojoule per mole, and that of nitrogen molecule is 946.0 kilojoule per mole. From this, we can identify that the number of bonds between atoms increases, the bond enthalpy also increases. That is, in hydrogen molecule, HH single bond is present. So the bond enthalpy is 435.8 kilojoule per mole. In oxygen molecule, oxygen double bond is present. So the bond enthalpy is high compared to that of hydrogen molecule, that is 498 kilojoule per mole. But nitrogen molecule contains nitrogen triple bond, so the bond enthalpy is higher than that of oxygen and hydrogen molecule. From this, we can identify that triple bond have more bond strength than double and single bonds. So the amount of energy is required to break 1 mole of triple bond is higher than that of double and single bonds. Next, bond enthalpies of some heteronuclear diatomic molecules are given. Heteronuclear diatomic molecules means molecules consist of two different atoms. Then for example, HF molecule, hydrogen fluoride molecule, the energy required to break the single bond between hydrogen and fluorine is 565 kilojoule per mole. Then it become hydrogen gaseous atom and fluorine gaseous atoms. Then HCl, bond enthalpy is 431 kilojoule per mole, and HBr, bond enthalpy is 362 kilojoule per mole, and that of hydrogen iodide, the bond enthalpy is 295 kilojoule per mole. That is, from HF to HI, bond enthalpy gradually decreases. From this, we can identify that all molecules consist of hydrogen with the same atomic size, but in the case of halogens, fluorine, chlorine, bromine and iodine, the atomic size gradually increases. When the atomic size increases, then the bond strength between this hydrogen and halogen decreases. Then from HF to HI, the bond strength gradually decreases, therefore the bond enthalpy also decreases. In the case of polyatomic molecules, the average bond enthalpy is calculated. Polyatomic means the molecule consists of more than one bond. For example, in the case of water molecule, it consists of two OH bonds. First, we break H single bond OH, then its bond enthalpy is 502 kilojoule per mole. Next step, we break the second O single bond H, then its bond enthalpy is 427 kilojoule per mole. From these values, we can calculate the average bond enthalpy, which is equal to total bond dissociation enthalpy divided by number of bonds broken. So here we substitute the values. Total bond dissociation enthalpy is 502 plus 427 divided by number of bonds broken is 2. So we get the value 464.5 kilojoule per mole. Next bond parameter is bond order. It is the number of bonds between the two atoms in a molecule. For example, hydrogen molecule, it contains one bond between two hydrogen atoms, so the bond order is 1. In the case of oxygen molecule, it contains two covalent bonds between two oxygen atoms, so the bond order is 2. Then in the case of nitrogen molecule, it contains 3 bonds between nitrogen atoms, so the bond order is 3. Then in the case of carbon monoxide molecule, there is 3 bonds between carbon and oxygen atoms, so the bond order is 3. So important bond parameters are over. Learn this Lewis symbol, limitations of octet rule and bond parameters carefully and prepare a note on this area.